Hi everyone. So as I promised, I'm going to put up the rest of 6.2 here so that you can see what we didn't do yet. If we take a look at inverse functions, and we had previously just talked about one-to-one functions, and that'll become important as to why we care about that in just a second. You'll understand why. So for inverse functions, what we're thinking about is here, if you look at the exploration, we can find the degrees Fahrenheit if we know the degrees Celsius, and we can do that by just plugging in and using the function that we have here. So if we do that, we need to find G of C here is equal to our degrees Fahrenheit. So if I want G of 100, what I'm looking at is 9/5 times 100 plus 32, which is going to be equal to 212. So what this gives me is if I have 100 degrees Celsius, then I'm saying that translates to 212 degrees Fahrenheit, right? So let's say I want to find G of C equals 112. Then that means that my degrees in Fahrenheit is 112, so I would have 9 over 5 times some C, some degrees in Celsius, plus 32. So if I subtract 32 from both sides, then I have 80 equals 9/5 C. And if I multiply both sides by 5/9, so that I can get the C value alone, by 5/9, then what I come up with is that C is equal to 44.4. So in this particular case, what I'm saying is that 112 degrees Fahrenheit is the same as 44.4 degrees Celsius. So what happens if you want to input degrees Fahrenheit consistently? Let's say I consistently measure my temperature in degrees Fahrenheit, but I want to find it in degrees Celsius. And so I need to reverse the formula and solve for C. So again, what I'm doing is F is equal to 9/5 C plus 32. So that means that F minus 32 equals 9/5 C. And if I multiply both sides again by 5/9, like I did before, then what I find is that C is equal to 5/9 of my degrees F minus 32, that whole quantity. Okay, so this is where it becomes useful for us to be able to find what we call inverses when we decide we want to solve, let's say, for one thing when we were solving previously for another. Here, we went from being able to find the degrees Fahrenheit from the degrees Celsius to being able to find the degrees Celsius from the degrees Fahrenheit. Okay, so if we suppose that a function is 1-to-1, the correspondence from the range of f to the domain of f is called the inverse function of f, and the symbol f, and then you've got an exponent, or it looks like an exponent, it's actually not. So the -1 is used to denote the inverse of f, and we actually say the inverse of f. So it is important to note that that's not an exponent, so we're not putting our original function inverse, basically reciprocal. So another way to say this is two functions are said to be inverses of each other if they are the reverse process of each other. Notice the exploration, the formula found in part C was the reverse process of G. So instead of inputting Celsius and outgoing Fahrenheit, our new function inputs Fahrenheit and outputs Celsius. So if we look at example 3 here, if we determine an inverse of a function, to find the inverse for the first one, where we have the students and their car. So right now for our original function for f, this is our domain, and this over here for f is our range. So if I'm looking at an inverse function, what I want to be able to do is find out what kind of car the person drives and figure out who that person is. So here, f is the the inverse of f. This is the domain. And this is the range for the inverse of f. Okay, so basically what we're doing is going backwards. We're coming over here, and we're saying if it's a Saturn, then Dan drives it. If it's a Pontiac, then John drives it. If it's a Honda, then Joe drives it. If it's a Chrysler, then Michelle drives it. Okay, so we're just flipping which order we go in. If I look at this, let's say it's a function, f of x here, then I know that my domain is equal to 1, 2, 3, and 4. And my range is equal to 5, 8, 11, and 14. So when I find the inverse of f, what I'm doing is my range from the original one becomes my domain. So the domain for the inverse is actually 5, 8, 11, and 14, while the range is equal to 1, 2, 3, and 4. So here, if I write out that set, what I'm going to have is 5, 1, and then the point 8, 2, and then the point 11, 3, and finally the point 14, 4. All right? So if we look at that, kind of going over again, since the inverse function, inverse of f is the reverse mapping of the function f, the domain of f is equal to the range of inverse f, and the range of f is equal to the domain of inverse f. Alrighty? So not too bad so far. This does explain why we want the functions to be one-to-one, and the only time that I can have an inverse function is when it's one-to-one. Because let's say if I come back up here, if I had more than one person, let's say Joe owned a Pontiac instead of owning a Honda, then if I looked at the Pontiac, I wouldn't be able to decide whether it's Joe or John. I would have two outputs for one input. So in order for us to have an inverse function, the initial function has to be one-to-one. Okay. So in fact, what f does to inverse f undoes, and vice versa. So f of inverse f of x is equal to x, and f of inverse f of x is also equal to x. And we can use this to verify that two functions are inverses of each other. So if we want to verify that these two functions are inverses of each other, what we can do is say that g of g inverse g of x, and here remember we're just going to input this is equal to, by composition of functions, this part, right? So the cube root of x minus 2. Now I'm going to substitute in this whole quantity right here in for the x in my g of x equation. So this is going to turn into the cube root of x minus 2 cubed plus 2, which is just going to equal to x minus 2 plus 2, which equals x. So we're good on that one, right? The next one we're going to do is we're going to look at the opposite. We're going to look at inverse of g of x. So we have inverse g of x. Put another parentheses there, and so that's g, inverse g of g of x this time is going to be this. So that's what we're going to put in here. So of x cubed plus 2. And now I'm going to substitute that in everywhere I have an x down here. And so what I have is the cube root of x cubed plus 2 minus 2 is equal to the cube root. And if you have the plus 2 and the minus 2, they cancel each other. So I have x cubed, which is just going to be equal to x. So we have shown that the inverse of g of x is inverse g of x, as those are written. If we look at using graphing utility, if you graph these three functions, what you'll see when you graph them is that the functions, we know that y minus x is, or y equal to x is equal to, just like this look right here, right? It's got a slope of 1 and it goes through the origin. So if this is x and this is y. If I look at y equals x cubed, so let me pick a purple, then I'm looking at something that goes up like this and then over and up like this, right? It's our favorite function. And then if I look at the graph for this, what I see is that it actually comes over this way and up and over this way. So this is our cube root of x, and this other one is the x cubed function. So what you see is they become a mirror image right across this line of y equal to x. Okay? So what we notice from number 2 is that the inverse functions are symmetric across the line y equal to x. Right? We can see the same thing if we graph the functions down here. Start with the same thing. If we have these functions, and so here again, I have my y equal to x line. And if I have a 2x plus 3 line, that means it's going to cross, put it here, at a positive 3, and it's got a slope of about 2, right? So if I look at that, it's got to be kind of like this. And if I look at the opposite, it's got a slope of 1/2, okay? And it's actually going to cross at negative 3, so let me go back and put some. So if I look at this one, what I have is it looks kind of like, yeah, it's hard to draw it. That should be at about negative 3. So they should be mirror images right across this line. So this one's the 1/2 x minus 3, and this one is the 2x plus 3. Okay? So you can see again, they're symmetric across the line y equals x. So that is interesting and it's helpful for us. Y equals x. All right, so the theorem that we have here on the top of the next page is that the graph of a one-to-one function, f, and the graph of its inverse, inverse f, are symmetric with respect to the line y equals x. So if we look at the graph here, for me this one was hard to see. You can look online. Basically what I did was, here I have my x, so there's a point right here that's negative 1, 0. So there should be a separate point that's 0, negative 1, which would be right here. And then there's a point up here that is 0, 3. So there should be a point over here that is 3, 0. And I don't like this because our x and y axes don't seem to be quite the same scale. And then if we look up here, I have 1, 4, and over here I would have out here at 4, 1, I would be right about here. This would be 4, 1. And so what I would have is just connecting the dots. Right. And if I do something right across, the way it works, to me it doesn't look very symmetric the way they did it because their scales aren't the same, but it should be symmetric across that y equals x line. Okay? The procedure for finding an inverse, let's talk about that because it is important, and this is on the exam. So first, we replace f of x with y, and then we interchange the variables x and y. This equation defines the inverse function f inverse implicitly. If possible, solve the implicit function for y in terms of x to obtain the explicit form f inverse. So we're going to have then y equals f inverse of x. And we'll go through this in a second. And then you can check the result by showing that f inverse of f of x and equals x, and that f of f inverse of x is also equal to x. Okay, so let's find the first one here on example. So if we say y is equal, let's put this out. I'm just going to replace my f of x with y. So I'm going to have y equals 4x plus 2. If I subtract, well, the next thing I do is I'm switching the variables, right? So I'm going to say x is equal to 4y plus 2. So this is step 1. Okay. Step 2, we're going to solve for y. So if I subtract 2 from both sides, I have x minus 2 is equal to 4y. And then if I divide both sides by 4, I have y is equal to x minus 2 over 4. And then all I'm really doing at the very end here for step 3 is I'm setting this equal to f inverse of x. Okay, and then I'm going to show that these actually work. So in step 3, I'm going to check my work. So I'm going to find f inverse of f of x, and that's going to be equal to f inverse of 4x plus 2, because that was our original function right here. Okay, so that's f of x, which this is equal to 4x plus 2 minus 2 all over 4. So that I have the plus 2 and the minus 2, so I'll have 4x over 4 equals x. I can do the same thing. Let me put it over here. So let's bring this up here just so we have room. If I look at f of f inverse of x for this one, then what I have is f of x minus 2 over 4. which if I substitute that into my original function, then I have 4 times x minus 2 over 4, and then I'm adding 2. If I multiply the two 4's, will cancel out, so I have x minus 2 plus 2, which is going to be equal to x. So here we have this as our original function, and we have right here this as our inverse function. If we do the same thing, and one thing to note is that the domain of our original function, the domain of f here was all reals, right? And the domain of inverse f is also all reals, so negative infinity to infinity. So we're good. We don't have any limitations there. All right. So if we want to find, let's say, a function where we have an inverse and the domain is somewhat limited, we have to be a little bit more careful. So here, if we look at f of x, let's start out with what my domain is. The domain for f of x is equal to all x such that x is not equal to negative 1, right? Because if x is equal to negative 1, then my denominator is 0, and we can't have that happen. So that's kind of what it says here. The function is 1 to 1, so we're good to go. And we also want to note that there is a vertical asymptote, because I can't cross anything out, at x equals negative 1, okay? So what we're going to do next, well, actually, we also want to note there's a horizontal asymptote here. If I look at the degree and just look at the first terms, there's a horizontal asymptote, right, at y equals 2 over 1, which is equal to 2. So at y equals 2, we also have a horizontal asymptote. So let's go ahead and go through the process of trying to find our inverse. So first we're going to set f of x equal to y, so we have y equals 2x minus 1 over x plus 1. We're going to switch the x and y's, so we have x equals 2y minus 1 over y plus 1. The second thing we're going to do is solve for y. So here what I want to do is multiply both sides by the y minus 1 term that's down here. So I'm going to have x times y plus 1, equals 2y minus 1. So I said that was a y minus 1, it's y plus 1. If I distribute my x, I have xy plus x equals 2y minus 1. I'm going to get both my y's on the same side of the equation. So I'm going to subtract xy from this side, I'm going to subtract xy from this side, and at the same time I'm going to move my 1 to the other side. So I'm going to add 1 over here, and I'm going to add 1 over here. So if I do that, what I have is x plus 1 equals 2y minus xy, right? Which this is equal to y times 2 minus x. So now I can solve for y by dividing both sides by my 2 minus x term, and what I end up with is y is equal to x plus 1 over 2 minus x. So here we should note that, let's set this go ahead and set this equal to inverse f. So this is inverse f of x, okay? And here we probably want to note that our domain is, I can't have the denominator equal to 0, so it's x such that x is not equal to 2. And if I look at a horizontal asymptote, you'll notice that we have this x and a negative x, so I'm going to have a horizontal asymptote, So there's a vertical asymptote here at x equals 2. I'm going to also have a horizontal asymptote at y equals 1 over negative 1, which is equal to negative 1. Now, if you take a second right here and look, you'll notice that my vertical asymptote and my horizontal asymptote had flipped. Okay? So that's kind of neat. So if I do one more thing here, and let me add just a page so that we have some room to do it.